So catalysis. So we've learned that rates of chemical reactions are affected by concentration and they're affected by temperature. But there are limits to both of those things. The limit on concentration could be the solubility of the compound. Right? You can't get past the solubility limit of it to increase the concentration further. Temperature can be a problem because if you get a high enough temperature, you could cause the reactants to decompose or cause damage to some surrounding system. So a catalyst can also affect the rate of a reaction, and it does so without being consumed. So this makes it different than an intermediate. An intermediate is formed and consumed. Formed and consumed, there's none of it left. The catalyst gets used and regenerated. Used and regenerated, or used and freed, right? And so at the end, the catalyst is the same. How does it work? It provides an alternate mechanism where the rate determining step has a lower activation energy. So here we have ozone and atomic oxygen reacting. And normally the transition state has a fairly high activation energy to get down here. When we add a catalyst, it causes the mechanism to change, so the activation energy is less. So it turns out chlorine atoms do this. They help ozone decompose into oxygen by creating a different pathway. So if we go back to the miniature golf analogy, so you're there trying to hit balls over this steep hump, and right next to it, there's a lower hump. It goes to the same place. Well, we could just hit them over that hump instead, right? Now it doesn't take as much energy to get them over. Another analogy I came up with is, I don't even know where I got this. A bunch of kindergarten kids and their teacher. They're going on maybe a walk through the woods, and they come across this fence, right? And they have to get over the fence. And the kindergartners are having a hard time climbing over the fence. So there's two possible ways you could think of an alternate pathway that's easier. The teacher could pick the kid up and lift him over, right? The teacher's just still there. Teacher doesn't get consumed in that. Teacher lifts him over. The teacher doesn't then go on down the path and leave everybody else behind. So that would be one way to think of catalysis. Or maybe the teacher sees that this is one of those split rail fences, and you can just slide that top rail over and drop it down and make the fence lower. Now they can all go over by themselves, and they go faster. Okay, so different ways to think of a catalyst. So in this mechanism for the catalytic destruction of ozone, atomic chlorine reacts with the ozone to form chlorine monoxide and oxygen. And then this interacts with atomic oxygen to reform atomic chlorine and oxygen. So if we look at the overall reaction here, canceling out things that appear on both sides. There were two things that canceled out. This is an intermediate. It was formed and destroyed. This is the catalyst. It was used and replenished. It became part of something and then got released, and at the end it's the same. So it doesn't get used up. It doesn't show up in the overall reaction as a reactant. For this mechanism, the activation energy for the rate-limiting step is a lot lower, and so the reaction occurs faster. And this is one of the things that's going on in the atmosphere. Where do chlorine atoms come from? Well, they come from the photodissociation of man-made chlorofluorocarbons. So these are the things like in Freon. And they get into the upper atmosphere, and the UV light causes them to dissociate. And so you get chlorine atoms. Chlorine is naturally a diatomic molecule, and so chlorine atoms are reactive, right? They're not going to just be happy. They're going to look for somebody to react with. And so they're hanging around, and one chlorine atom can catalyze lots and lots and lots of ozone destruction. We hear about the theft of catalytic converters a lot. That's one way people are trying to, I guess, earn a living. What is a catalytic converter? It's a piece of your car that has a catalyst in it. And those are typically platinum, rhodium, or palladium. And those metals are expensive, and that's why people want the catalytic converters. It has one of these metals on a high surface area substrate, just a thing to hold that with a high surface area. As your exhaust fumes pass over that, these catalysts cause the pollutants in your exhaust to be converted to less harmful substances. So instead of nitrogen monoxide and carbon monoxide, we can catalyze the reaction to form nitrogen and carbon dioxide. Air is mostly nitrogen. So putting more nitrogen in the air, no problem. Carbon dioxide is also a significant part of the atmosphere. So both of these are fine. NO and CO, though, not good. It also promotes the complete combustion of fuel fragments. So when the fuels burn, because nothing happens perfectly, most of it burns, but then some pieces of it don't burn. Like, you think about a wood burning in your fireplace, right? And, after it's all done, sometimes there's little chunks of wood along the side, right, that didn't quite burn up. Well, we don't really want those floating around in the atmosphere either. And so the catalytic converter can also promote the complete combustion of those to carbon dioxide and water. So there's chemistry trying to help the air be cleaner. There's different types of catalysts and catalysis. Homogeneous and heterogeneous. Prefix homo means the same, and hetero means different, right? So in a homogeneous catalysis, the catalyst and the reactants are in the same physical state. So catalytic destruction of ozone by chlorine, all of that occurs in the gas state. The catalyst is in the gas state, and the reactants are in the gas state. Heterogeneous catalysis, the catalyst is in a different physical state than the reactants. So the catalytic converter, you have your pollutant gases coming out as gases, but the catalyst is a solid. So that's a heterogeneous catalysis. Oops, pushed the wrong button. So we hear a lot about ozone depletion and the ozone hole, right? And we're all concerned about our environment and greenhouse gases and carbon footprint and all of this stuff. It's actually a lot more complicated than the news media and politicians would have you believe. So heterogeneous catalysis, actually, is most likely responsible for the formation of an annual hole in the ozone over Antarctica. Wrong button. So in May, looking at Antarctica, it may look like this, and in September, it looks like this. So this is the hole. There's this big hole. And you could look at that and get really alarmed, like, oh my goodness, we're going to perish by next summer, right? This is bad. But then miraculously, the next May, it looks like that again. Well, what's going on? Well, there's chlorine evenly distributed throughout the entire atmosphere, because gases are nice that way. They just mix really, really well. So why should we see a drop in this particular location that's seasonal? Well, chlorine from those chlorofluorocarbons gets bound up in other substances, like ClO, NO2. And when chlorine reacts and gets stuck in something like this, it's like, hey, I'm okay now. I've got my guys around me. My electrons are happy. I don't need to go out and destroy ozone today, right? So it's not going to catalyze ozone destruction. But when we get these polar stratospheric clouds, they have ice particles in them. The ice particles catalyze reactions that release the chlorine. So, here's chlorine, happy in his little compound here. And with those ice particles, gets made into chlorine gas. In the Antarctic spring, there's more sunlight down there. Sunlight dissociates the chlorine molecules into chlorine atoms. And these guys are going to go chew up the ozone. And this is going to keep going until those stratospheric clouds melt. So as a result, we've got an ozone hole that forms every spring. It lasts 6 to 8 weeks, and then it goes away again. Right? Any questions about that? I think it's safe to say there's still a lot of cool research to be done on the environment in chemistry. I mean, there's still so much we don't know. Another place that catalysis is important is in the hydrogenation of double bonds. So carbon-carbon double bonds will react with hydrogen, but they do so quite slowly at normal temperatures. But if we have the catalyst, platinum, palladium, or nickel, finely divided, little tiny particles, that causes the reaction to occur very rapidly. The large activation energy of the reaction, because of this strong double bond, is lowered when that substance adsorbs onto the surface of the catalyst. So here we have this ethene. Two carbons with a double bond, and then each carbon has 2 hydrogens on it. When it adsorbs, and that's a gas sticking onto a solid, this ethene and the hydrogen are going to diffuse on the surface. They're going to move around on the surface until they run into each other. And then a reaction can occur, and then the product desorbs from the surface. So this is the surface of the catalyst. This is not down deep in the catalyst. They're stuck on the top, and they're just kind of scooting around. And I am not going to test you on the very gritty details of these. This is just to give you an idea of what kinds of catalysis are possible, and that it's something we need to keep in the back of our minds. super important catalysts are enzymes. Most of the reactions that are needed to occur in your body or in the growth of a plant occur at a rate that's too slow to support life. You can't just heat it up because that's going to destroy other things. So enzymes are biological catalysts. They're generally large protein molecules. And the reactant molecule is going to bind to what's called an active site on the catalyst, the enzyme, through intermolecular forces. And when this happens, the activation energy of the reaction is greatly decreased, and that increases the rate of the reaction. So here we have our substrate. This is the thing that's going to react. So here we might have this binding mechanism. The substrate and the enzyme will bind together, and that will happen quickly. And then this complex will break into products and the enzyme, and that's going to be the slower step, the rate-limiting step. So this active site on the enzyme is very specific for certain molecules. There might only be one molecule that's going to fit in there because of the shape of the protein and where the different hydrogen bonding atoms and stuff are. Other things aren't going to fit in there. But when that substrate comes, it's like, oh, this is like, it fits me like a glove. I'm going to just come in here, and it's just all these nice intermolecular forces. So this is something that occurs in the digestion of sugar. So sucrose, table sugar, needs to be broken down into glucose and fructose. And that happens by breaking this carbon-oxygen bond here. Well, that happens very slowly at body temperature. But when sucrose binds to the active site of the sucrase enzyme, and most of the enzyme names end in ASE, and the first part is related to the things that they bind with. So sucrase bonds with sucrose. When sucrose binds in here, there is strain put on that bond. It's like it comes in, and to get all those other intermolecular forces just right, it has to kind of tweak itself. Kind of like if you're like reaching for something and then somebody pushes you and your back goes out, right? Because you were in a bad position, right? So it's getting stretched and that bond is weakened. And so now it's much easier to break, and it'll break faster. So biochemistry is really pretty fascinating. You learn about all the different chemical reactions that are occurring in the body, and then your body needs to control them, right? Do we always want to hydrolyze all the sucrose that we get in? When do we need to make insulin? When do we need to make this hormone or that hormone, right? Enzymes control those things. The enzymes are very specific. They catalyze just a single reaction. And they're tremendously effective. It can speed up a reaction by a factor of as large as 1 billion. That's a lot faster. There are substances that inhibit enzymes, keep them from working. If you lock up one enzyme molecule, that could possibly prevent the reaction of billions of substrate molecules. So if you're trying to kill a certain insect, say, if you can find something that's going to inhibit an important enzyme in that insect and not in the other living things around it, then you can kill just the insect that you're trying to kill and not hurt everybody else. Of course, sometimes we find out later that it does hurt everybody else.